Let me go ahead. The instructions for number 25 read, use the error formulas in theorem 4.19 to estimate the error in approximating the integral with n equal 4. N is the number of divisions I'm going to divide it up into if I were to draw in trapezoids or whatever is going on in the different approximation things. And they want us to do it with the trapezoidal rule and the Simpson's rule. So we are not finding the values. These are going to go faster. We're just saying if we use those formulas, what would be the error we got? The advantage of maybe thinking about it this way in checking the error first is if you know, since they're such a pain to do, right? If you know the error is less with one way than the other by checking the error first, then you could just pick the way that would give you the least error and go back and do it that way is the thought, okay? So that's why they're not making you do all that work. I picked 25 because if they want us to do A, the trapezoidal rule, and then B is going to be Simpson's rule, okay? So let's start with the trapezoidal rule. The trapezoidal rule error formula, both of those formulas are on page 313 in your book, and I'll write it down. It says the error for the trapezoidal rule on A is less than or equal to B minus A, and if you look at the theorem, I'm not going to write it down because it'll take up the whole iPad to write it down, but the B minus A are the upper and lower boundaries, so we're going to subtract the upper lower boundaries and cube them over 12n squared, and is the number of divisions we would make if we actually drew these trapezoids out and solved it, you know, the long, hard way. And then we multiply it by the maximum of the absolute value of the second derivative. Okay, now, so I can tell that I got to go take this, at least the second derivative. And if you glance down at the Simpson's rule, you see that you got to actually take the fourth derivative. So let's just do all that at once and get on a roll with taking derivatives so we don't have to take a few, go back and take a few more, okay? So that's what I did when I work these. In this section, is I go ahead and say, okay, what was the function? The function was this f of x here, 1 over x minus 1. This is the function we're talking about. And part of what I got to plug into this is the maximum of the second derivative and then the maximum of the fourth derivative, okay? And again, the book kind of explains a little bit about how they come up with that, but it really, some of the stuff, they don't even go into the proof of it because it's beyond what we can understand, okay? So let's say if the function is 1 over x plus 1, remember if I take in derivatives, I would probably want to rewrite this as x plus 1 to the negative 1 power, because when you take the derivative, you know, we have we usually do it with that chain rule, right, where okay, so if I take the derivative, f prime of x, let me change to a different color, red is not an ideal color here, you would say you drop the number out front, so the negative 1 comes out front, I'll just put it as a negative, and then you add, you put your term down, x plus 1, and then you subtract 1 from your exponent when you take the derivative. Remember, this is confusing because we're doing integrals and we're doing derivatives, and it's all getting kind of mushed together, but this is to the negative 2 power, right? So now I need to take the second derivative. I'm actually going to go all the way through the fourth derivative, so I have all this information handy. So if I take the second derivative, it's negative 2 times that negative out front, which becomes a positive 2. And then you write x plus 1 to the negative 3 power, right? Because you're subtracting 1 every time. When I go to the third derivative, I'm going to write a little f3 of x there instead of making those marks. That's what most times they do anyway. So again, you take this exponent of negative 3 on the second derivative, you drop it down out front and multiply it by the constant out front. Negative 3 times 2 is negative 6, yeah, x plus 1 to the negative 4th power. And then the last one I'm going to have to look at is this f4 of x. Negative 4 times negative 6 is 24, x plus 1 to the negative 5 power. So I've got my fourth derivative. Now, if you notice in this formula, they're asking me for the maximums of the second derivative and the maximum of the fourth derivative. You know, there's some other ways to do this, but most of what they're doing in the book is looking at the graph. So you've got a graphing calculator. Let's go calculate all. Let's go figure this thing out. Okay, here's one thing you're going to have to know. We're only looking, when we look at these graphs, aren't we only looking between 0 and 1, right? because those are my boundaries. So I got to keep that in mind when I'm looking for my maximum. So if we let's go put the second derivative on the calculator. So go y to the y equal and type in 2 times x plus 1 raised to the negative third power. And look at the graph. And we're only looking between 0 and 1. And if you look at your calculator, and you need to be doing that or this is not going to make a lick of sense if you're not looking at your calculator and putting it in. Where does the maximum occur between 0 and 1?
0.
At 0. It's a decreasing function. It's coming down. So our maximum is at x equals 0. So if I want to find that really quickly, I could go to the table of values and save myself some time. I could do the second, I could do I could do something else, but the quickest way to do this is since it's at 0, that point is 0, 2. That means my maximum value is 2 there. So I'm going to use that when I calculate, the trapezoidal formula. Now I'm going to need to do the same thing because I can see both of the formulas sitting there in the book. And so just to save ourselves some time and work efficiently, let's go put in the fourth derivative formula into the calculator. It is 24 times x plus 1 raised to the negative fifth power. And we're only looking between 0 and 1. So when I go graph it, I'm going to keep that in mind. Same thing. The maximum is going to occur at 0. Yeah, if you go to the table, you got the point 0.24 here. So my maximum on the Simpson's formula is going to be 24. So we're going to use our calculator to find that instead of beating it to death, which we could do. And we're not, we want to work smart here. Okay, so I've got these values, and I'm going to move to a different slide now because we're, I'm out of room. But let's do the trapezoidal rule first. My error, I know the formula tells me my error is less than this amount here, and it gives me the formula that where I can plug stuff in. That's a 3 there. It didn't turn out looking too much that way, the way I wrote it. Now, if my error is less than this, which they give me in the formula, I forgot to put that. And again, it says A less than X and B. They're assuming that your upper boundary and your lower boundary in the correct order there. If your error is less than that, the instructions said to calculate it with n equal 4, and we can figure out what kind of error we're going to have. So all we got to do is plug in the information we know now. And this will go faster because we've got the pieces. My error is going to be less than or equal to, now I was going from 0 to 1 on my integral. That was 1 minus 0, which is 1. I'll just kind of go ahead and just write all the pieces in. And then 12 times n squared, they told me to calculate it with 4, which didn't take up there, but n is 4. So let's see, 4 squared is 16, and 12 times 16 is, 192, right? Yeah, okay. So I have 1 over 192. Well, actually, that was 1 cubed, which ended up being 1, right? Okay. And then I got to multiply it by the maximum of the second derivative, but I already calculated that. And the maximum of the second derivative was just 2. So the error is less than or equal to 2 over 192. So if you divide 2 over 192 out, you get, well, it's 1 over 96. But we'll go ahead and put it as a decimal value. They actually, I'm always telling y'all don't do it, but here they're actually kind of take it out to, it's like this, but they're actually rounding it. What do they do? Yeah, they're rounding it to the nearest hundredth. That looks like I'm not sure. I think they must have done this because I checked my answer. I think I would have made a note if it was, they write it's like 0.01 in the answer key, I think.
0.0104. 6667.
Yeah, okay, yeah. So, and then they rounded. I think they rounded to the nearest hundredth, which is why I didn't catch that I messed up because I checked my answer and I'm like, that rounds to the same thing. So yeah, it was 2 over 192. I forgot to multiply by 2 before I divided it out. So that is the error that we would get with the trapezoidal formula error. And for Simpson's, it's a lot of the same stuff. It's just a slightly different formula for error. Says E is less than or equal to, and again, it's going to be an open book test because I don't know how you would remember these formulas too much. Well, there's no way, I don't think. I mean, I guess you could, but, and it's the maximum of the fourth derivative, and it's the absolute value. We don't care whether it's a negative number or a positive number. We're just looking at let me put a 4 there. So basically, you're copying the formula down, and so B minus A, 1 minus 0 is 1 to the 5th power, and 1 to the 5th power is 1 on top. Your N is still 4, so it's 4 to the 4th power.
That's 256.
Okay, so that's 1 over 180 times 256.
That's
And we got to multiply by the maximum wasn't the maximum 24, is what we calculated earlier, right? Okay, so we got to multiply by 24, so we're just going to stick this in the calculator. And I better multiply it out and make sure that I didn't mess that one up too and not catch it. Okay, I get 5.208 with a repeating 3 times 10 to the negative 4th, and if you move that back 4 spaces, you end up getting 0.0005. We'll just stop there, because we rounded the other one a lot less accurately than that.
basically Simpsons